works. Okay, we're going to look at kinetic energy. Okay? And kinetic energy can take many different forms, right? So listed a whole bunch in your textbook: heat, light, nuclear energy, chemical energy, we get stored energy. Right? And you all know, or you should know, that energy can be transferred from one form to another form to create motion. So Dominic is the perfect example, right? She got on a choo-choo train all the way over the pond. The airplane was converting jet fuel into heat. The heat was driving a turbine, and the turbine obviously generates thrust, which then creates motion, and that's how you got safely across the water. If the jet fuel had run out, the turbine would have stopped spinning, there would have been no more thrust, and Dominic would have swam her way to the Seychelles.
Yeah.
So energy is transferable, okay? Now for energy to exist, usually work needs to be done, right? So if you consider an object in motion, right? So let's consider Toya, you on your skateboard, right? On your skateboard, while your skateboard is moving, you have energy, right? You have kinetic energy. Because you are moving, you have some form of potential kind of energy, right? But where did that energy come from? Why do you have this kinetic energy? Where did it come from? How did you get moving? You had to work. You had to apply some friction force against the ground with your foot to propel yourself forwards. And the amount of work that you did is actually exactly the same as the amount of kinetic energy that you will have at that particular moment. Now, obviously, there's friction, and so your kinetic energy can deplete, obviously. But if you imagine yourself on a completely frictionless surface, the amount of work that you put in to propel yourself forward to get to a certain velocity, if you stay at constant velocity because there's no friction or air, in a perfect world, right? The amount of work you put in will be exactly equal to the amount of kinetic energy that you have. Right? So that's why we learned about work, and when you see the unit for energy is going to be the same, that's why we learned them first, okay? Because work and energy go hand in hand. So just like work, obviously energy is scalar, right? In other words, it doesn't have direction. It can be negative and positive to indicate something, but it's scalar, meaning it only has magnitude, right? You can't have -2 joules of energy technically, right? You can't have negative energy. It just doesn't exist, right? It's like having negative speed. What does that mean? In terms of speed, we don't consider negative speeds, right? If we talk about a vector, a negative speed just means that you're going in the opposite direction, okay? Right, now we are only going to be considering mechanical energy, so we don't have to worry about heat or light or anything like that. So fortunately for us, mechanical energy only has two forms. It can either be kinetic or potential, right? So kinetic energy means that it's the energy that something, why don't I not make it up? There we go. It's the energy that a body possesses because of its motion. The fact that you are moving means that you have energy, okay?
So
they are directly related. In other words, if you are not in motion, you don't have any kinetic energy. You don't have any potential for energy transfer, okay? Because you are motionless. Okay? Now we're going to look, obviously tomorrow, we'll look at potential energy, but potential energy is the energy that something might have, right? So if you consider holding a ball up, the ball is not moving. But by the mere fact that if you let it go, gravity will pull it down, it has some potential to do energy. So it doesn't have any energy, but it has the potential to do energy. Another easy thing to think about with potential energy is a spring, right? So if you have a spring that's sprung down, it's not moving, so it has no kinetic energy, but because it's compressed, the moment you release it, it has the potential to do something. Okay, so that's potential energy. Kinetic energy obviously is directly related to motion, meaning that if you are moving, you have kinetic energy. Okay? And again, the reason we look at it is because we need to remember that energy is transferable. Okay? Right, now, because kinetic energy is directly related to motion, we can obviously consider velocity to be one of the key components of what we're going to use as our calculation, and not acceleration anymore, right? Because remember, we don't have to be accelerating to be moving. Acceleration just means a change in velocity, right? So not like force, where we were looking at acceleration, when we're considering energy, just like momentum, right? Momentum again was directly related to the fact that if you were moving, you had some momentum, okay? And again, momentum doesn't care if you're accelerating or not. Right? If you are moving, you have momentum, and if you are moving, you also have some form of kinetic energy. So here's the formula. There is a very scientific way to directly relate work done. How do we calculate work done? It's force times distance. What is force? Force is mass times acceleration, all right? And here's kinetic energy, right? So kinetic energy, we take mass times velocity squared, divide by 2, right? So half mass times velocity squared. Now I'll show you later on, not now because it's not something you need to know, but fun, I'll show you how we can use integration to go from work done to energy, right? Because what's the integral of acceleration? If we go back up the chain, velocity. Yeah? So I'll show you at some point how we can get to 2. Now let's have a look at the units on the right. Okay, so if we consider mass is in kilograms. Okay, velocity is in meters per second. Okay, except this is velocity squared, so we're going to have mass times meters per second squared. Everything gets squared, so the mass gets squared, the seconds get squared. And what we can do is we can pull one of those m's off to the side. You see how I've done that? I've just attached it over here. So here we had both of our m's. I've just pulled one of them off to the side. And what we're left with is kilograms meters per second, which is the whole definition of 1 Newton, okay? But we still have this extra m. So we have Newton meters. And we just learned in our last lesson that 1 Newton meter is the same as 1 joule. Okay? And so that is why work done and energy, right, are both measured in joules. Okay? They actually have the same units. Right? And we can, outside of the scope of this course, actually go between energy and work done. And you can see where the formula for this comes from. So they just give it to you. It's unfortunately one of those things where they just say, okay, well, here's the formula. This is how you use it. Right? But that's not a nice way of learning something. I think it's more fun to see where something comes from, because then you actually understand it better. So we will look at that. We'll look at it next week when you guys are, and Dominic's also back in the land of Namibia. Okay, so all forms of energy are measured in joules, not just kinetic energy, potential energy, heat, everything's measured in joules, right? Some kinds of energy are measured in another unit. Usually it's some form of chemical energy that goes on inside of you. Who can take a guess? Starts with a C. Everybody like that's on a weight watching program is always talking about this magical C word.
Oh, calories.
Calories, okay? Calories is a form of energy, okay?
Yep.
So you can go and have a look at how it's calculated. It's not directly linked to joules though, okay? You measure calories in joules, right? It's just a human way of measuring energy transfer. Okay.
Mr. James,
Yes, boss.
I have a fun fact.
A fun fact. Share your fun fact.
Do you want to know what one of the most calorie-dense forms of food is
Go.
per gram? Nuts.
Yes, well, that does make a lot of sense. Nuts. That's why if you eat too many of them, you get such a sore stomach.
Yep.
Cool. Okay. So we're all happy with kinetic energy. Okay. So think of kinetic energy. If you are in motion, you have kinetic energy, right? And just remember that some kind of work had to be done in order for you to be in motion. You don't just get into motion like magic, right? Something has to happen. In other words, some force had to be applied to the object in order to get it in motion, right? And that force had some form of work. Okay, let's look at some simple examples. Okay, so we have to remember our formula now. So kinetic energy is equal to half mass velocity squared, velocity squared. Okay. We have a body of mass 3 kilograms moving at 5 meters per second. Okay, so the first thing you need to do is have a look at the units that you're given. Okay, so the mass of my body is given in kilograms. Do I like kilograms? What do we measure mass in? Well, no, remember this formula uses mass, but what particular mass does it use? Mass in kilograms. Yeah, so you need to make sure that the units you've given here are in kilograms. If they're not, you need to convert first. Okay? Otherwise, you're not measuring in joules, you're measuring in something else. Okay? That's, remember, the whole definition of a joule is the movement of a force of 1 Newton to move an object 1 meter. Okay? So if you're measuring in grams, that's not a joule. Maybe it's a microjoule, mini joule, I don't know. Okay, so simple questions like this are obviously nice and easy. You can imagine you're never going to get these easy questions, but they're nice to get you into the habit, right? So we have a half, the mass is 3 kilograms and the velocity is 5 squared. Now, do you see why energy is scalar? Which unit over there is the one that is a vector quantity? The velocity. And what happens to anything when you square it? Take any number in the world, it will always become positive, right? And so you can never get a negative number out of this, right? You can put in a negative velocity, but the negative velocity is going to square itself and become positive. And so that's why kinetic energy is always going to be a positive number, okay? So very simple, a half times what? 25 times 3 divided by 2. What do we get? 37.5. And what are we going to use? Joules, right? You can also use Newton meters if you want, but that's not the normal convention. The convention is to use joules. Okay, okay, let's move on to another little problem. Okay, we have a ball of mass, I'm going to highlight it, 50 grams. Hits the ground with a speed of 10 meters per second. Right? So just before it hits the ground, it has some form of kinetic energy. It rebounds with a speed of 6 meters per second. Find the loss in kinetic energy. Okay, so obviously when the ball rebounded, it didn't have the same amount of energy going up, right? Where did that energy get lost? Remember, energy is transferable. It's not actually lost. Yeah, so either to the ground. What kinds of energy do you think might have been transferred? What do you think it's going to do when it hits the ground? It's going to make a sound. Sound is a form of energy, right? Right. Some heat might have been generated with the ball hitting the ground. So there's heat, sound, right? Vibrations, friction. So there's many forms of energy that could have been transferred, right? So actually the question is wrong. It shouldn't be the loss of kinetic energy that occurs. It should have been the transfer of kinetic energy, or they could have said the loss of kinetic energy from the ball. Okay? Yeah. No energy can ever be lost. All energy is transferred. So even if something loses energy, it's losing that energy, but it's actually transferring it to something. Okay? So if we want to find the loss of energy, right, what's the easiest way to work that out? So if we want to find our final kinetic energy, how can I calculate that? So if we want to find a change in something, in anything in life, we take the final something minus the initial something, and we get the change. So what if I want to find the change in your age from last year to this year? Well, I'll take your age this year, subtract your age last year, and I'll get your age difference. Okay, so if I want to find the final kinetic energy, I can just take, sorry, not the final kinetic energy, the change in kinetic energy. We can take the final kinetic energy and we can subtract the initial kinetic energy. Okay. So I'm going to do this in 2 stages to avoid a very stupid oops that some people make by being lazy. Okay, so I'm going to use change in kinetic energy. Right, my final kinetic energy. Okay, what's the formula for kinetic energy, Tony? mv squared. Okay, so to find my final kinetic energy, I need to go and look at what the kinetic energy was before or after. Before it bounces, or after? After, because final. I mean, I'm making it sound stupid, but I really want to be pedantic about how you have to read the question. Just see which is the final and which is the initial. Okay, what do we call final velocity? How do we normally label it? V. Okay, so we have a half mv squared, and we're going to take away a half m u squared. Okay, u is velocity, right? It's just initial velocity. Okay, so this is the velocity of that ball, exactly this fraction of the second before it actually hits the ground. This is how much kinetic energy it had, and the moment it hit the ground and bounced back up, that's our final kinetic energy. Okay, do I know the mass of the object? Are you sure? I need to convert it. So we have 50 grams, that's equal to 0.05 kilograms. Now I have the mass, and now I can do the calculation. So I am going to have half 0.05. We're going to have velocity, which is 6 squared, and we're going to take away half 0.05 times 10 squared. What do I get, Zara? 0.9. 2.5, so that will give us minus 1.6. Okay, so what does that minus 1.6 mean? Because remember we said energy is scalar. It's the amount that was transferred. So if you get a negative change in kinetic energy, that just means that this object lost or transferred some of its kinetic energy elsewhere. Okay, what if this number was positive? It gained kinetic energy. So give me a stupid scenario where you could have gained kinetic energy. Come on, Zara, you're Indian like me. What do we love watching? What do all Indians watch? Cricket. Yeah, when a batsman strikes a ball, he might strike the ball and it might leave at a greater, well, actually they don't always do, leave at a greater speed than when it first hit the bat. And so there would have been a gain in kinetic energy. Okay, so there's an example where even though the velocities are in different directions, remember kinetic energy doesn't care about the direction, it only cares about the quantity. right? So it's your speed is the determining factor. So actually, technically, couldn't we just say m speed squared? Because we don't care about the direction of the velocity. We care about the speed that it's going actually. Right. They did bring this up in the textbook. I can't imagine anybody making this mistake unless, actually, I can imagine Keanu making this mistake because he likes to get a little bit too clever sometimes. So what a lot of people would do is they would say, okay, well, all that's happened here is a change in velocity. And so they might, before they plug anything into the equations, just subtract the velocities from each other. Okay. So I just want to show you, you can do that. So here's our two formula again. Here's a half mv squared minus a half mu squared. Right? And we can factor out the half m, and we're left with v squared minus u squared. Right? What some people make the mistake of is they say, I'll just take my final velocity minus my initial velocity and square that. Yeah, but remember, that's not the same thing, because if I expand this out again, I get this. And they are not the same thing. And they are completely different things. I don't think this is anything. That's nonsense. Right? So if you are calculating a change in kinetic energy, my advice would just be work them out separately, because then you don't even get in the situation where you make this silly mistake. The same thing happened. I don't know if you guys remember when we did integration and we were looking at the volume when you rotated something, because we had something squared, we had the function squared because it was pi r squared. The temptation was to subtract the two formula and then square it, but it was actually one squared minus the other squared. So if you are going to be one of those that wants to take shortcuts, just bear in mind this one. Okay, well, as far as kinetic energy goes, guys, that's it. Okay. So this is one of those things that we're learning because you can imagine we're going to use it later on. So we're going to learn about, learned about kinetic energy. We're going to learn about potential energy. And the most important thing I want you to take away from this lesson is, one, obviously work had to be done to create this energy, kinetic energy. And two, all energy is transferable. So it can be transferred from one object to the other. Okay. So those are your homework questions for the day. It shouldn't take you very long. Dom, do you have your textbook with you?
I do not.
Do you want me to send you the digital one so you have it on your phone?
Yes, please. Then I can use that for the rest of the week as well.
Cool. So I'll quickly WhatsApp that to you. Then you'll have your mechanics textbook. And again, like I said, none of these questions are really tricky, right? But I want you to remember that some of the questions that you do are going to be based on the previous topic, right? So you might see things like work done and things like that. And I want you to remember that in order for kinetic energy to exist, work had to happen, right? So some force had to be applied to get the object moving, right? And that work is exactly proportional to the amount of kinetic energy the object will have initially, right? So that question might read like, a force of some newtons was applied to move an object a certain distance, right? Meaning they're telling you how to calculate the kinetic energy, right? And then they might give you its final velocity and then say, find the gain or loss. So just because we're not looking particularly at work now, don't forget about how we calculated it. And in fact, everything we've learned in mechanics it started off with learning what acceleration, velocity, initial velocity, displacement were in order to get us to this point.